Every cubic meter of the cosmos contains close to 1 billion minute particles, known as neutrinos, that were created in the Big Bang. Neutrinos are invisible to us, but they could hold the answer to one of the biggest unsolved questions of physics. Why is there matter in our universe? The European spallation source, ESS in Lund, Sweden, will at 5 megawatts be the world's most powerful accelerator. It will be the brightest neutron source in the world. The ESS Neutrino Super Beam Facility, ESSnuSB, an extension of ESS, will explore the difference between matter and antimatter by comparing neutrino and antineutrino oscillations. Neutrinos exist in 3 flavors, together with their antiparticles. For ESSnuSB, the beam power will be doubled to 10 megawatts to also generate the most intense neutrino beam in the world. The power upgrade of the ESS LINAC will enable 14 3-millisecond pulses of hydrogen ions per second to be accelerated. The electrons of the hydrogen ions will be stripped away and the resultant protons injected into a 400-meter circumference accumulator ring where the pulses will be compressed to 1.3 microseconds and directed toward a target station. When the protons hit the target, pions are produced and focused by a magnetic horn. The pions decay into muons and muon neutrinos in a 30-meter decay tunnel. The muons will be stopped at the end of the tunnel, whereas the neutrinos, which rarely interact with matter, will continue their journey through the ground toward the detectors. A near detector monitors the beam, and an underground far detector situated 500 kilometers to the north of ESS measures the neutrinos. The muon neutrinos will change flavor on their journey, oscillating between the 3 neutrino flavors, muon, electron, and tau, as illustrated, where the relative proportions of the different neutrinos are seen to oscillate up and down as they travel from ESS to the far detector. The oscillating red line shows the electron-neutrino signal that we are interested in. The second maximum at 460 km distance, where the ESS measures, is more pronounced than its first maximum at 170 kilometers, where the other proposed experiments plan to measure. Our far detector will contain 1 million tons of water in 2 large vessels, located in a mine 1,000 meters underground level. Although neutrinos are very penetrating and difficult to detect, the large mass of the far detector and the intense beam from ESS will ensure that some interact with nuclei in the water, producing charged particles that can be detected either muons or electrons. As these particles travel through water, they emit so-called Cherenkov light. Using sensitive detectors mounted on the walls of the detector vessels, the ring pattern produced by Cherenkov light is detected as illustrated, and the flavor and energy of the incoming muon or electron neutrino will be determined. Data will be collected over 10 years, using both beams of neutrinos and antineutrinos. By measuring the number of electron-neutrino-like interactions for these 2 cases, we can investigate any difference in oscillatory behavior of neutrinos and antineutrinos. If a difference can be established, this will provide decisive clues to the mystery of why precisely equal amounts of matter and antimatter created in the Big Bang have led to a universe containing matter, stars, planets, ourselves, and not only radiation. Current theory predicts that the matter and antimatter created in equal quantities very rapidly annihilated each other, producing radiation. If so, today we would expect the universe to contain only radiation. There must have been a subtle asymmetry between matter and antimatter that occurred just after the Big Bang, resulting in a surplus of matter after the almost total global matter-antimatter annihilation. The ESSnuSB design study project, supported by the Cost Action EuroNewNet and by the EU Horizon 2020 programme, is being carried out by an international collaboration of researchers from 17 different institutes in 11 European countries. The study will produce a conceptual design report for the project by 2021, later followed by a complete technical design report. ESSnuSB construction on the ESS and phar detector sites will start some years later and be ready for data collection around 2035. On completion, the ESS neutrino superbeam facility will be the leading neutrino beam experiment in the world. As such, it will attract scientists from all over the globe.